Today, we're going to talk about the internet's unsung heroes. I'm talking about TCP's smart traffic cops. These are the clever rules that basically stop the entire network from grinding to a halt every single time you stream a movie or download a big file. So let's get right into it.
It really all comes down to this one big question. I mean, think about it. Every time you're watching something online or downloading a huge game, you are relying on a system that has to be both unbelievably fast and at the same time super careful. So how does it walk that tightrope? Well, the whole secret is in how it handles traffic jams. And that leads us right to the main challenge for any data network, really, congestion. Before we can get into the solutions, we first have to wrap our heads around the problem itself.
So what even is congestion? Well, it's not a broken cable or some kind of hardware failure. The best way to think about it is just a temporary traffic jam. A router, somewhere out there on the internet, gets totally overwhelmed with data. Its little waiting room, its buffer, fills right up, and it has no choice but to start dropping data packets. It's just overloaded. Simple as that. Okay, now here's the absolute key point you have to understand about traditional TCP, which, was designed for wired networks. If a computer sends out a data packet and it doesn't get that little, "Hey, I got it" message back, that's the acknowledgement, or ACK, it makes one single critical assumption. The network must be congested. All right, so if TCP's first guess is always congestion, how does it deal with it? It uses a strategy that honestly sounds a little weird at first, but it's incredibly powerful and also extremely cautious. It's called slow start. What's so interesting is just how methodical this whole process is. See, TCP doesn't just jump back in and start sending at full speed. Nope. It uses something called a congestion window, which is just the number of packets it's allowed to send at once. It starts that window at just one single packet. When it gets the ACK back for that one, it doubles the window to 2, then 4, then 8. You see the pattern. This exponential growth lets it carefully, but also pretty quickly, test the network to find out what the new safe sending speed is. But what happens if it gets a bit too ambitious, pushes too hard, and another packet gets lost, causing a full timeout? Well, TCP slams on the brakes. Hard. It cuts its own speed limit, that's the congestion threshold, in half, and it resets its sending window all the way back down to 1. It's a really blunt tool, forcing the whole connection to start that ramp-up process from scratch. And this leads to a really important question. Is that full slow start always the right move? I mean, what if the problem wasn't some massive network-wide gridlock? What if it was just a single lonely packet that got dropped because of some random minor glitch? Using slow start in that situation is kind of like shutting down an entire highway just because one car got a flat tire. There's got to be a smarter way, right? And of course there is. This is where two really cool related mechanisms come into play: fast retransmit and fast recovery. Together, they give TCP a much more sophisticated way to handle these little hiccups. So here's the really clever part. Even if one packet goes missing, the computer on the other end might still be getting all the packets that came after it. And when it does, it keeps sending those ACK messages. This continuous stream of acknowledgements is a huge clue. It tells the sender that the path isn't dead. Data is still getting through. Okay, take a look at this diagram. It shows exactly what's going on. Let's say packet number 3 gets dropped, but the receiver gets packets 4, 5, and 6 just fine. For each of those, it sends an ACK back, but it keeps saying, "Hey, I'm still waiting for packet number 2 to be followed by 3. These repeated messages are called duplicate ACKs, and they act like a laser-guided signal, pinpointing for the sender exactly which packet went missing. This is the fast retransmit part of the equation. As soon as the sender sees this pattern, usually it waits for 3 of these duplicate ACKs, it doesn't bother waiting for the slow timeout timer to expire. It knows exactly what's missing, and it resends that one packet right away. It's like a surgical fix instead of a total shutdown. And that is the whole idea behind fast recovery. Because the sender is still getting those duplicate ACKs, it has proof that the connection is actually pretty healthy. This is a strong signal that there isn't any major congestion, so there's absolutely no reason to hit the panic button and trigger a drastic slow start. The sender can just patch the one missing piece and keep things moving. This slide really lays it all out, side by side. A timeout where everything just goes silent is treated like a major accident. It triggers slow start. But if you duplicate ACKs, that's seen as a minor issue. It triggers fast recovery, which keeps the data flowing at speed. It's the difference between a full stop and just a quick little lane change. And you just can't overstate how big a deal this is. By intelligently telling the difference between a small single packet loss and a major network jam, fast transmit and fast recovery stop all those unnecessary slowdowns. And as the source material says, this improves the efficiency of TCP dramatically. So let's just quickly pull all this together. Slow start is the cautious, by-the-book approach for starting up or for recovering from a big mess. Fast retransmit, that's the clever detective that spots the one missing piece of the puzzle. And fast recovery is the efficient mechanic that just swaps out the bad part without stopping the whole assembly line. And when you put them all together, you get a system that is both incredibly tough and remarkably efficient. But here's a final thought to leave you with. All of these rules we've talked about are built on that one core assumption. A lost packet means the network is congested. That works great on reliable wired networks. But what happens on wireless connections, Wi-Fi or your cell phone, where packets get lost all the time for other reasons, like interference or you just walk out of range? How does TCP's logic hold up then? Well, that's a whole other can of worms, and maybe a topic for another day.